In this video, we'll be reviewing the computation of volumes through cross-sectional areas. There are three other methods we'll need to learn, and those are volumes by disks, washers, which is an extension of disks, and shells. No matter the method we need to implement to compute volume, we will always follow the same guideline. Slice, formulate, and integrate in that order. More specifically, we want to slice some cross-section of the shape we're computing the volume of. We'll then formulate the area of some cross-section, and then we'll integrate to receive the desired volume. This is because if we integrate an area function, our integral will be in terms of the next dimension. Area is two-dimensional, and volume is three-dimensional. Let me show you how to use this guideline for cross-sections in the following example. The base of a solid is bounded by y equals x, y equals 0, and x equals 3. Cross-sections of the solid perpendicular to the x-axis are squares. Compute the volume of the solid. So before we begin, it's always great to visualize exactly what we're looking at. So here we have y equals 0, y equals x, x equals 3 on this graph. And this graph is a little skewed to show you a third dimension. So I'm attempting to show you this third dimension with what I have. So they stated that cross-sections perpendicular to the x-axis are squares. So we're taking a look at the x-axis here. And if we were to look perpendicular, since the x-axis is going left-right, perpendicular means up-down. So if we're looking at cross-sections perpendicular to the x-axis, this is exactly what we should see. If we were to make a cross-section, let's say somewhere around here, right? If we were to go right here, we should see a cross-section that looks like a square. Just like that. Now, if we look at any other cross-section, we could keep going. We could look at somewhere over here. We could look at this cross-section. Again, we should see a square, or as close as we can get to a square with my horrible drawing. And if we were to look at any cross-section between 0, so this is x equals 0 and x equals 3, if we look at any cross-section, we can take this one over here as well, we would also see a square. That is what they are saying. That if we were to look at any cross-section, so essentially, if we were to add up all of these cross-sections, we would receive a solid. So let me draw one more, just so we completely understand how many squares there are, because there are an infinite amount of squares. And we can draw one more over here. I'm just saying that there are so many. So many right there. Cool. And so if we were to put together all of these two-dimensional squares, every single one of them as infinite as they are, we would receive a solid that has a volume and not an area. So we have already completed that slice portion. We have sliced some cross sections. We only really needed to do one, but it helps us to see a lot. So we have sliced. Up next, we need to formulate. We need to formulate the area of each cross section in terms of the variables that we're given. So to formulate, let's see, pick any square, doesn't matter. If we're looking at, let's say, this middle square right here, what would the area of this square be? Well, let's think about it for a second. Remember, squares have equal sides, and the area of a square is the side squared. So, how can we represent the area with the variables that we're given? Well, let's think about it. The side, one of the sides actually, the left side of these squares actually runs along our plane. And we see that the length right here is the distance from the x-axis all the way to y equals x. And so what this means, guys, is that the distance or the side length, s, is equal to the distance from y equals x to the x-axis. So the y equals x, we can just say that that's x minus y equals 0, or 0. So again, the distance from y equals x to y equals 0. And the reason I'm doing these in terms of x is because we're going left to right. They told us perpendicular to the x-axis. Had they told us perpendicular to the y-axis, this would be a whole different situation. So just keep that in your head for now. If they say perpendicular to the x-axis, we're looking at vertical cross sections. just like we see here. And so our side length is equal to the distance from the x-axis to the curve, and we see that that was x minus 0. And so our area can be rewritten as not s squared anymore, but x minus 0 squared, or x squared. So our area equals x squared, because we will do x times x, which gives us the area of each cross section. And there we go. That's the formulating part. Now for the integrating part. When we integrate, we want to go ahead and do the following. We will always compute the definite integral from the lower bound, so I'm going to say a, to our upper bound b, and we will be integrating our area function. And since this is with respect to x, I'm going to use the area as a function of x, so a of x. And from here, guys, we can just go ahead and replace everything. And this works for every single one, whether it's disk, cross-sectional areas, washers, shell method, doesn't matter. We are computing the definite integral from the lower to upper bound of the area function with respect to x. And we will do so after we slice and formulate. So our lower bound here was 0, x equals 0. That's where it intersects on the left, and we see that it intersects on the right at x equals 3. Our area function, guess what? We already wrote it out. It's x squared. And then we're computing with respect to x. And again, guys, the definite integral, when we're computing the definite integral, we are summing all of these infinitely thin squares to get the volume. And this dx right here, this dx represents the differential of x, or the infinitely thin width of each of these squares. There's side, 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 and then the width, how thin it actually is. And so when we multiply an area times a width, that will give us volume. So that is what I want us to see there. I hope we are seeing that. And now we can go ahead and finish this bad boy off. So the definite integral from 0 to 3 of x squared dx is equal to, well, the antiderivative of x squared will give us x cubed over 3. And we will be computing this antiderivative from 0 to 3, fundamental theorem of calculus. So that will be x cubed, so 3 cubed, which is going to be 27, divided by 3 will give us 9. And then we'll subtract at 0, so 0 cubed over 3, that'll just be 0. 9 minus 0 gives us 9. And so our volume of the solid, so the volume of the solid will be 9 cubic units. It will be cubic units. Realize that this is not a 2-dimensional figure anymore. This is a 3-dimensional figure once we add up all of those areas. And there we go. We sliced, formulated, and integrated our way to the correct answer. We can apply this guideline to all volume problems, and I'll prove it to you in the videos for the other volume computation methods. Until you get there, watch our example videos for cross-sectional volumes and continue your path to mastery. Thanks for watching.